Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR NET, GATE, NT exam, PhD exam, SET exam, Jest, Tifr, IIT-Jam and other exams related to physical science. Okay, so this is the 7th part of this series in which we are discussing CSIR NET Physics PYQs of December 2017. Okay, so also I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures which are going to help you to crack exams related to physical science. Okay, so I'll start with first question. Okay, this is the 7th part of the series of CSIR NET Physics PYQs of December 2019. Okay. Okay, so question number first. Assume that the noise spectral density, the noise, these are part C questions guys. Okay, assume that the noise spectral density at any given frequency at any given frequency in a current amplifier in a current amplifier is independent of frequency of frequency the bandwidth of measurement the bandwidth of measurement is changed from 1 hertz to 10 hertz. The ratio A upon B of the RMS root mean squared. Okay, noise RMS noise current RMS noise current before. Okay, so RMS noise current before A, that is A. Okay, and after RMS noise current after, that is B. Okay, this is before changing and this is after changing the noise current. Okay, B, the bandwidth modification after B, the bandwidth the bandwidth modification, is. Okay, options are very simple question, and this is part C question, guys. 1 upon 10. Option B is 1 upon root 10. Option C is root 10. Option D is 10. Okay, so this is the question. The question is, assume that the noise spectral density, okay, the noise spectral density at any given frequency, okay, the frequency is given at any given frequency in current amplifier is independent of frequency. So noise spectral density doesn't depend on frequency, okay, okay, and the bandwidth of measurement. So the bandwidth of measurement is changed from 1 hertz. Initially it was 1 hertz, and we have changed it to 10 hertz. Okay, so changed from 1 hertz to 10 hertz. The ratio of RMS noise current before and after the bandwidth modification is. Okay, so you need to find out the ratio of RMS current before the modification and RMS current after the bandwidth modification, that you need to find out. So very good question, and only it is a formula based question. Okay, so there's a formula, guys, very simple formula. So the current the RMS noise current, okay, that is RMS noise current is proportional to bandwidth. Okay, B, bandwidth. So RMS noise current is proportional to square root of bandwidth. Okay, so so from here it means A is noise RMS noise current before uh, the modification, and B is after the RMS noise current after the modification, that is going to be root B1 upon B2, where B1 and B2 are bandwidth. Okay, simple. So from this, okay, this is very important one. The noise current, RMS noise current is proportional to the bandwidth. Okay, so A upon B, this is the current RMS noise current before modification, and this is RMS noise current after modification is going to be root B1 upon B2, where B1 and B2 are bandwidth, right? So it means A upon B is going to be, okay, before modification the bandwidth was 1 hertz, right, 1, and after it was 10 hertz, right, after modification. So it was changed from 1 hertz to 10 hertz, right? So this means A upon B is going to be 1 upon root 10. Okay, 1 upon root 10. So which option is matching, guys? Just a formula based question, and this is 5 marks question, guys. Okay, so option B is the correct option. Okay, 1 upon root 10. 1 upon root 10. Okay, next question, guys, question number 2. Question number 2 is, meanwhile just let me check whether I'm audible or not. Okay, so there's a formula. Absolutely, yes, I'm audible. So I'm going to start with second question now. Very good question, guys. Second question. So it's a question from quantum mechanics. Let the normalized eigenstates eigenstates of the Hamiltonian of the Hamiltonian okay, the normalized eigenstates of the Hamiltonian H is 210, 120 and 002. Hamiltonian B psi 1, psi 2 and psi 3. Okay, so let the normalized eigenstates of the Hamiltonian is given in the matrix form. Okay, Hamiltonian B psi 1, psi 2 and psi 3. Okay, the expectation value H, okay, expectation value of Hamiltonian H and the variance and the variance H, variance of H, okay, in the state psi, with the value of psi is given, that is 1 by root 3, then psi 1 plus psi 2 minus iota psi 3. Okay, so this is given, and options this state of this are, okay, and options are 4 by 3 and 1 by 3. Option B are 4 by 3 and 2 by 3. Option C are 2 and 2 by 3, and option D are 2 and 1. Okay, so this is the question, guys. Very good question. Let the normalized eigenstates of the Hamiltonian be psi 1, psi 2, psi 3. Okay, the expectation value of H and the variance of H in this state psi equal to 1 upon root 3 psi 1 plus psi 2 minus iota psi 3 are, and these are the options given. Okay, very good question. I'm going to solve it. So first we have been given Hamiltonian, right? So Hamiltonian is given, that is H equal to 210, 120 and 002. Okay, so this is the Hamiltonian which is given. Okay, so now we'll find eigenvalues. Okay, eigenvalue. So eigenvalues, we can find it. So this is going to be determinant of H equal to 0, right? So eigenvalue is going to be, we'll find the determinant of this. So this is 2. So that means eigenvalue means that is a minus lambda I, right? That is H minus lambda I. Determinant of H minus lambda I equal to 0. If you put that, then we'll get the eigenvalues lambda 1, lambda 2, lambda 3, right? Okay, so this is going to be 2 minus lambda 1, because here we'll write identity matrix, right? So then we'll subtract it. So it is going to be 2 minus lambda 1 0, I have already explained it in my matrix classes, right? In my mathematical physics classes, where I have explained matrix. Okay, I have explained matrices. So 1, 2 minus lambda 0 and 0, 0, 2 minus lambda. Okay, so this determinant is going to be 0, right? So we'll solve it further. So it is going to be, so we are going to solve from here, okay, this side, because then these two are 0, so then it will be easy for us. Okay, okay, so this is going to be 2 minus lambda, 2 minus lambda. Okay, this one, and this 2 minus lambda whole square minus 1, right? So 2 minus lambda whole square minus 1 square, right? So this equal to 0. So this is going to be 2 minus lambda. I will open it. So a square minus b square, right? So this is going to be 2 minus lambda, 2 minus lambda plus 1 into 2 minus lambda minus 1 equal to 0, right? So this is going to be 2 minus lambda into this will be minus lambda plus 3, and this will be minus lambda plus 1 equal to 0. So value of lambdas are 2, 1 and 3. Okay, so it means lambda 1 equal to 2, lambda 2 equal to 1, and lambda 3 equal to 3. Okay, so these are the values of lambda 1, lambda 2, lambda 3. So eigenvalues are eigenvalues of matrix, right? Eigenvalues of matrix of Hamiltonian are the that eigen value energies, right? So E1, E2. So it means E1 is 2, eigen values are energy eigenvalues, right? So these are energy eigenvalues. So lambda E1 equal to 2, E2 energy E2 equal to 1, and E3 equal to 3. Okay, so E1, E2, E3 value we have found. Okay, 2, 1, 3. Well, now we have been given this psi. Okay, psi is given 1 upon root 3 psi 1 plus psi 2 minus iota psi 3, right? So this is psi 1 plus psi 2 minus iota 3. Okay, okay. So we have energy eigenvalues. So now we will solve it. So we have been given psi 1, psi 2, and psi 3, the value of psi, right? So we can write it 1 upon root 3 psi 1 plus 1 upon root 3 psi 2 minus iota 1 upon root 3 psi 3. Okay, these are the this is the wave function. We can write like this. Okay, so from here we can see from here, right? C1, that is P1, that is probability for first excited state, the ground state, right? P1 equal to mod C1 square, right? The coefficient of this is 1 upon root 3 whole square, right? 1 upon 3. Similarly, P2 is mod C2 square, right? Coefficient of psi 2, so 1 upon root 3 whole square. So this is going to be 1 upon 3, and P3 is going to be C3 mod C3 square, the coefficient of psi 3. So that is going to be 1 upon minus 1 upon root 3 whole square. So this is 1 upon 3. Okay, So these are the P1, P2, P3, right? Now we know the energy eigen, how to find that expectation value of H, right? So expectation value of H is going to be, expectation value of H is going to be, we know this is sigma Pi EI, right? So this is going to be P1 E1 plus P2 E2 plus P3 E3, right? So this is going to be P1. P1 is 1 by 3 into E1 is given, right? 2 plus P2 is 1 by 3, E2 is given, that is 1 plus P3 is 1 by 3 and E3 is given, that is 3, right? Because values of E1, E2 are this one, right? So we'll solve it. So this is going to be, this value is going to be 2 by 3 plus 1 by 3 plus 1, right? So this is going to be, or just 3, right? This is going to be, if we solve it, so this value is going to be 2, okay? So the value of expectation value of H we have found, right? That is 2. Now, now we will find H square, okay? So expectation value of H square, okay? So expectation value of H square is going to be, that is sigma, you need to note down, okay? This is sigma Pi EI square, okay? Pi is EI square. So it means P1 E1 square plus P2 E2 square plus P3 E3 square. Very important formulas, you need to know. You must know it, okay? This one, okay? So, okay, expectation value of H square. So this is going H square, right? So this is going to be expectation value of H square equal to 1 by 3 into 2 square plus 1 by 3 into 1 square plus 1 by 3 into 3 square. 1 by 3 into 3 square, okay? So this is the expectation value of H square, okay? So we'll solve it. So this value is going to be 4 by 3 plus 1 by 3 plus 9 by 3, okay? And this value is going to be 14 by 3, okay? So this is the value of H square, right? So now we have to find, because expectation value of H we have already found, right? And now we have to find that is variance of H, right? This is given in the question, that is variance of H in the state psi we have to find, right? So variance of H means that is delta H square we need to find, or we can say delta E square, right? That we need to find, and that we know that is expectation value of H square minus expectation value of, this is the variance formula, right? Variance and standard deviation, we know that very well, right? So this is expectation value of square of expectation value of H square, right? Square of expectation value of H, right? So this is going to be this value below 14 upon 3 minus expectation value of H we know, right? And that is 2, that is 2 whole square, that is 2 square, right? So it is going to be 14 by 3 minus 2, right? And this value is going to be 2 by 3. So expectation value of H is 2, and the variance of H is 2 by 3. So which option is matching, guys? Let me check which option is matching. Option C is the correct option, guys. Okay, 2 and 2 by 3. Option C. Okay. Yes, correct. Next question, guys. These are very good questions which I am solving. Okay. Next question. Next question is question number 3. Very good question, and it's from thermodynamics. Okay. For a crystal, that is a solid state physics, I would say. So it is for a crystal. Mixed question. For a crystal, for a crystal, for a crystal, let phi denotes phi denote phi denote phi denote the energy, denote the energy required, the energy required to create to create to create a pair of vacancy, a pair of vacancy, a pair of vacancy and interstitial defects, and interstitial defects, okay, a pair of vacancy and a pair of interstitial defects. If, very good question, guys. Okay, if n pairs of such defects means interstitial defects. Okay, such defects are formed and n is less equal to capital N and N dash. Okay, capital N and N dash, where N and N dash are, where N and N dash are respectively the total number of lattice lattice and interstitial sites and interstitial sites, total number of lattice and interstitial sites, then n is approximately options are root n dash e to the power minus pi upon 2 kt. 2 kt, k is Boltzmann constant, right? kbt or kt we can write, kt. Option B is root n dash root n dash e to the power minus pi upon kt. Okay, option C is 1 by 2 n plus n dash e to the power minus pi upon 2 kt, and option D is 1 by 2 n plus n dash e to the power minus pi upon kt. Okay. Okay, so I'm going to solve it. So before that, I'll read it for you. Question, very good question. Okay, for a crystal, so we are talking about a crystal. Okay, let phi denote the energy. Phi denotes the energy required to create a pair of vacancy. Okay, so phi is the energy which is required to create a pair of vacancy and interstitial defects. Pair of vacancy and a pair of interstitial defects. Okay, that is the energy. If n pairs of such defects are formed, okay, so n pairs of such defects are formed, and n is very less than n, where n and n dash are respectively the total number of lattice and interstitial sites. N dash is total number of interstitial sites and n is total number of lattice. Okay, then n is approximately, so you need to find n. Okay, the value of n. Okay, so I'm going to start. So first, thermodynamic probability of such defects is, so we need to know that this formula. Okay, so thermodynamic probability of such defects. Okay, thermodynamic 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 probability thermodynamic probability thermodynamic probability of such defects Okay, thermodynamic probability of such defects, that is W. Okay, W is a formula, that is n factorial upon n minus n factorial into n factorial. Okay, and into n dash factorial upon n dash minus n factorial into n factorial. Okay, so this is the thermodynamic probability which you need to note down, guys. Okay, so this is the thermodynamic probability of such defects, that is n factorial upon n minus n factorial into n factorial into n factorial upon n minus n factorial and n factorial. Okay, so n dash factorial, right? So n dash is the total number of defects, and n is the total number of lattice. Okay, total number of interstitial defects. Okay, and n is the number of pairs of defects, interstitial defects. Okay, so the thermodynamic probability is n capital N factorial upon capital N minus n factorial into n factorial into capital N dash factorial upon n dash minus n factorial into n factorial. Okay, very important formula, you should know it. Okay, well, next, this is W. So now we'll find that is change in entropy, guys. Okay, change in entropy formula we know, right? So change in entropy is, that is delta S. Change in entropy, delta S is, we know that is K ln omega or ln W, right? ln W. W is the thermodynamic probability, a microstate, right? Right. So now, so delta S is going to be K ln omega, that is W, right? So that is going to be n factorial upon n minus n factorial into n factorial into n dash factorial into n dash minus n factorial into n factorial. Okay, so this is the thermodynamic, this is the change in entropy, right? We'll solve it. So this is going to be delta S equal to, delta S is going to be equal to, this is going to be, so we'll solve it, right? So ln, so we can write ln n factorial plus n factorial, right? We know the log property, and by Stirling formula we can write ln n factorial equal to almost approximately equal to n ln n, right? So we are using this, so this is going to be k n ln n plus n dash ln n dash n dash ln n dash minus n minus n, okay, minus n n dash minus n, this is n minus n dash ln n minus n minus n dash minus n dash minus n ln n dash minus n minus 2n ln n. Okay, this is very simple. We know log property, right? This is going to log n factorial plus log n factorial minus n log n factorial, right? Log n minus n factorial, right? But and also with that we have used Stirling formula, right? So this is n factorial value is going to be n ln n, almost equal to, okay? So that's why I have written directly, okay? So this is the value of delta S, change in entropy, okay? So change in, now we'll find change in free energy in creating n defects, okay? So change in free energy, change in free energy in creating, in creating n Frankel, n Frankel, n Frankel, n Frankel defects. Okay, so change in free energy in creating n Frankel defects. So that is the defects, interstitial defects, okay, Frankel defects. So this is going to be delta G equal to n phi, the energy required for creating a pair of vacancy or defects, right? That is phi, n phi, and then n is number of pairs, n phi minus T delta S. Okay, very important formula. So we need to note down. This is the change in entropy we know. Okay, so this is change in free energy. Okay, so now we will put the value here. Okay, so this this is going to be delta G. Delta G is going to be equal to n phi minus T delta S, right? N phi minus T delta S. So T will remain it is, and we will put the value of delta S, right? So this is going to be K ln. This is we have found, right? K ln, this one. K ln K K n K n ln n, okay, plus n dash ln n minus n minus n ln n minus n minus n factorial minus n ln n, sorry, n dash minus n, okay, ln n dash n minus 2n ln n, okay, this one. So this is the value of delta G. So we have to find that n, right, value of n. So since we know, so for that what are we going to do? That is delta G upon delta n equal to 0. Okay, so delta G upon delta n is going to be 0. This is del. So del upon del n, delta G is going to be 0. Okay, we'll put del upon del G upon del n equal to 0. Okay, so now we'll put this value. So this is going to be del upon del G. Okay, so we'll just put the value. So we'll differentiate it. So this value is going to be, to differentiate this delta G with respect to n. Okay, so this is going to be, we differentiate it, very simple differentiation. Okay, so you can use it. So this is going to be phi, n is phi, right? Phi minus kt, right? There is a kt ln after differentiation. Okay, so this is going kt ln n minus n minus n into minus n upon n square. Okay, this is going to be 0. So this is the value, n dash n minus n minus n kt phi minus kt ln n minus n into n dash minus n upon n square, right? So now we have given, since n is very less than n and n dash, right? So this is given. So this implies n minus n almost equal to n, and n dash minus n almost equal to n dash, right? So we'll put the value here. So this is going to be phi minus kt ln n dash upon n square is going to be 0. So this means, or we can write it phi minus kt, and this is, we can write ln n root n dash upon n whole square, we can write, right? So this whole square, so equal to 0, and from here phi is going to be equal to, this is log property, right? 2 kt ln root n dash upon n whole square. right? So from here, ln root n dash upon n is going to be whole square will not be, because this is we have opened it by, so we've used a log property, right? So ln is going to be equal to pi upon 2 kt, right? So from here, the value of root n dash upon n is going to be e to the power pi upon 2 kt, right? E to the power pi upon 2 kt. So from here, value of n is going to be, you can really find the value of n. Value of n is going to be root n dash e to the power minus pi upon 2 kt, right? Because n will go there, n will come in denominator of root n dash, and we will take into numerator, right? And then the sign is going to be minus, right? So this is the answer, guys. Very important question and very lengthy one as well, but easy. Okay, so which option is correct matching? So option number A is matching, guys. Okay, this one, root n dash e to the power minus pi upon 2 kt. This one, root n dash e to the power minus pi upon 2 kt. So this is the correct answer, guys. Okay, good question. Next question, guys. Okay, question number 4. Question number 4. Okay. Question number 4 is, in a circuit diagram is given. Question number 4, in a circuit, in the circuit diagram, in the circuit diagram of a band pass filter, shown below, band pass filter shown below are equal to 10 kilo ohm. Okay, R value is given 10 kilo ohm. Okay, and I will make a diagram in next page. So in order to get a lower cutoff frequency, lower cutoff frequency of 150 hertz, and upper cutoff frequency of 10 kilohertz, the appropriate values, the appropriate values of appropriate values of C1 and C2 respectively, C1 and C2 respectively are option A 0.1 microfarad and 1.5 nanofarad, option B 0.3 microfarad and 5.0 nanofarad, option C is 1.5 nanofarad and 0.1 microfarad, option D is 5.0 nanofarad and 0.3 microfarad. Okay, so these are the options. Now I'll make a diagram. So this is the band pass filter, guys. Okay, band pass filter. This is the capacitor C1. Okay, and this is R1, grounded, and this is RF. This is R, and this is C2, grounded, another amplifier, RF, output. Okay, so this is the band band pass filter, guys. Okay, band pass filter. This is given. This is the band pass filter which is given. Okay, this is R1, C1, C2, and this is R. Okay, so this is band pass filter. Okay, so in the question, in the circuit diagram of band pass filter shown below. Okay, so this is the circuit diagram of band pass filter. Okay, and now in order to get lower cutoff frequency of 150 hertz and upper cutoff frequency of 10 kilohertz, the appropriate values of C1 and C2 we need to find out. Okay, very simple question, formula based question. Okay, so I'm going to solve it. So first, a lower cutoff frequency of high pass filter. Okay, lower cutoff frequency, lower cutoff frequency for high pass filter. Okay, lower cutoff frequency for high pass filter. Okay, so lower cutoff frequency for high pass filter will find that is that we know that is given. Okay, so that is equal to value is 1 upon 2 pi RC1. Okay, 1 upon 2 pi RC1, and that is given, that is 10 hertz. Okay, so lower cutoff frequency of high pass filter, okay, that is 10 hertz. Okay, that is given. So this means 1 upon 2 pi RC1 equal to 10 hertz. Okay, so this is formula, very important formula, you need to know. Okay, lower cutoff frequency of high pass filter, that is 1 upon 2 pi R1. Okay, 2 pi RC1. Okay, value of R is already given, 10 kilo ohm. Okay, well, so this is 10 hertz, 10, right? So from here value of R1 is going to be C1 is going to be 1 upon 2 pi, that is I'll put the value of 2 pi, it is 3.14 into value of R is 10 kilohertz, means 10 into 10 to the power 3 into 10, right? That is the C1, and if we solve it, so this value is going to be almost equal to 0.1 microfarad. Okay, now similarly higher similarly higher cutoff frequency higher cutoff frequency of low pass filter, because a low pass filter, because we know that band pass filter is made from lower cutoff frequency of high pass filter and higher cutoff frequency of low pass filter, right? So higher cutoff frequency of low pass filter is that value we know, 1 upon 2 pi RC2. Okay, 1 upon 2 pi RC2, 1 upon 2 pi RC2. Okay, so this is the formula for, so lower cutoff frequency 1 upon 2 pi RC2, right? And that value is given 10 kilohertz. 10 kilohertz. 10 kilohertz means 10 into 10 to the power 3. Okay, 10 into 10 to the power 3. So this is going to be then from here value of C2 is going to be 1 upon 2 pi, the value is 2 pi value we know, that is 2 into 3.14 into 2 pi, this is RC2, R value R is 10 into 10 to the power 3, that is R 10 kilohertz, right, into 10 into 10 to the power 3, 10 kilohertz, right? So this is going to be, so this value is going to be almost equal to 1.5 nanofarad, right? Okay, nanofarad. Okay, so so these are the answers. So which option is matching? So we need to find just the value of C1, C2. So which option is matching, guys? Option number A is matching, guys. Okay, option number A is matching, that is 0.1 microfarad. Okay, 0.1 microfarad and 1.5 nanofarad. So this one 0.1 microfarad and C2 is 1.5 nanofarad. Okay, very good. good question. Next question, guys. And this is also very good question from nuclear physics. Okay. Question is, question number 5, formula based question, right? The Beath-Weizsäcker formula, Beath-Weizsäcker formula, okay. The Beath-Weizsäcker formula for the binding energy for the binding energy which is in mega electron volt, okay, MeV, of nucleus of atomic number Z and mass number A is 15.8 A minus 18.3 A to the power 2 by 3 minus 0.714 Z into Z minus 1 upon A to the power 1 by 3 minus 23.2 into A minus 2Z A minus 2Z whole square upon A minus 2Z whole square upon A, okay. The ratio of Z upon A for most stable isobar of A equal to 64 of A equal to 64 nucleus is nearest to options are option A is 0.30, option B is 0.35, option C is 0.45, option D is 0.50, okay. So this is the question. The Beath-Weizsäcker formula for the binding energy in MeV of nucleus of atomic number Z and mass number A is given, okay. So this is the formula, okay, and this is atomic number, this is given, okay. Binding energy is given. The ratio of Z upon A for the most stable isobar of A equal to 64, whose atomic number is 64 nucleus, okay, is nearest to that, you need to find out. Okay, so this is Coulombic constant, this is asymmetric energy constant, and this is that surface energy constant, this is the volume energy constant, right? Okay, so I'll solve it. So there is a there's a formula, guys, and you can easily solve it. You need to note down and remember it. Okay, so you can easily solve these type of questions quickly. The formula is so we need to find the ratio of Z upon A for the most stable isobar, okay, of A. The value of A is 64. Okay, so formula is Z not equal to, or Z equal to A upon 2 plus AC upon 2AA A to the power 2 by 3. Very important formula, guys. 5 marks question, right? Very important formula. A by 2 to the power A by 3. Okay, A to the power 2 by 3. Okay, so this is Z Z equal to Z not equal to, okay, which we need to find out this one. So Z not equal to A upon 2 plus AC upon 2A, AC upon 2AA into A to the power 2 by 3. Okay, note down, guys. Okay, this one. So now we can write Z upon A, that Z naught upon A is going to be 1 upon 2 plus AC upon 2AA that is the asymmetric energy constant, okay, into A to the power 2 by 3. Or from here we know we have given AC is given, AC is given, AC is this guy, okay, Coulombic constant. So this is 0.714 0.714 0.714, and this is A, right, asymmetric energy constant. This is 23.2. A is given, AA is given 23.2, 23.2, 23.2, 23.2. Okay, so Z naught upon A, we'll just put the value. So 1 upon, okay, 1 upon 2 plus AC value is 0.714 upon 2 into 23.2, okay, A to the power 2 by 3, okay, or this is going to be Z upon Z naught upon A equal to Z naught upon A equal to 1 upon 2 plus 0.015 A to the power 2 by 3. Okay, so this value is, if you calculate this value, so this value is going to be 0.015, 0.015. Okay, and this is also the formula, guys. This also you need to know down directly, okay? Those two formulas, this one and this one. Okay, this is also very important formula. You can directly solve questions of 5 marks, okay, if you know this formula. So Z naught upon A is going to be, now we'll put the value 1 upon 2 plus 0.015, and value of A is given, right, that is 64, 0.015 into 64 to the power 2 by 3. right? So we'll solve it. So this is going to be 1 into 2 plus 0 0.015 into, we can write 4 to the power 3, right? So this is going to be 4 square, because 4 to the power 3, 3 will get cancelled, 4 square, and if you solve it, this value is going to be 0.45. Okay, so this is the answer, guys. So this formula and this formula you need to know. So we have found the ratio of Z upon A for this. Okay, so the ratio of Z upon A for the most stable isobar of A equal to 64. Okay, that we need to find A equal to 64. So this is the answer. Okay, so which option is matching, guys? Let me check. Option C is the correct option, guys. Okay, guys, so before ending the class, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free lectures which are going to help you, which are free live lectures which are going to help you to crack the exams related to physical science. Okay, okay, guys, thank you. Bye.